Hi everyone, I'm Eldy Lazaro, a third-year PhD student at the Atlas Institute in CU Boulder. Today I'm excited to present our open-source Desktop Biofibers Spinning Machine. As some of you might know, smart textiles seamlessly integrate fabrics with electronic materials such as conductive threads through advanced textile structures like weaving or knitting. The Levi's Tracker jacket made with Jacquard by Google is a good example of a smart textile. Sensor grids are woven into the cuff of the jacket, transforming the textile into a dynamic interface that recognizes gestures and facilitates touch-based interactions. The smart textile industry is projected to be worth more than $18 billion by 2030, indicating significant potential for innovation and growth. However, this industry poses significant environmental risks by combining two highly toxic waste streams, textile waste and electronic waste. To tackle some of these environmental challenges, there is growing interest within the HCI community in exploring sustainability initiatives such as design for disassembly or design for repair when developing soft electronics. Particularly, interest is growing in using bio-based materials as scaffolds for embedding electronics, with a focus on promoting awareness for the end-of-life sustainability of soft electronic devices. When intentionally exposed to biodegradable conditions, these bio-based scaffolds encasing electronic components degrade, facilitating the release and recycling of the embedded electronics. While often limited to sheets or molded form factors, the tunability of bio-based materials present an opportunity for seamless integration into textile structures. Our approach to sustainable smart textile design aims to support the integration of bio-based materials in textiles, particularly at the foundational level of textiles fibers. The inspiration for our machine came from recognizing the need for accessible tools and workflows in fiber design. This addresses the challenge of tunability, replicability, and exploring the use of bio-based fibers for sustainable smart textile applications. Current fiber spinning prototyping relies on machines that can take up a whole room. These machines are often inaccessible to smart textile innovators due to their size, cost, and the specialized knowledge required for operation. As seen here, I'm up on a ladder, filling the tank of a wet spinning machine with liquid spinning solution, giving you a glimpse of the scale involved. Due to these constraints, we have developed a desktop-sized spinning machine with corresponding elements from a lab-scale wet spinning one. Our machine is open-sourced, low-cost, and built with modular parts, allowing for the rapid prototyping, production, and customization of bio-based fibers, or biofibers for short. Now let's explore the main components and functionalities of our machine. We used the open-source large volume extruder syringe pump on our machine to facilitate extruding viscous liquid solutions. The silicone heater wrap allows to keep the bio-based spinning solution deposited inside the syringe, maintain a stable viscosity before extrusion. The heated nozzle enables the spinning solution to be heated to a specific temperature at extrusion time. The 3D printed rollers or collectors rotate smoothly on a linear rod, controlled by user-specified revolutions per minute. They are supported by a latch mechanism ensuring stability during rotation and easy removal post-spinning. Each collector is paired with a 3D printed basin, serving as a multi-purpose container for both fiber production and subsequent steps, facilitating processes like coagulation along with post-production processes like finishing, drying, and treatment. As biofibers wind around a collector, they are coated with the solution in the basin. Our material exploration, as detailed in the paper, has been supported by the current setup of the machine. This exploration has focused on a series of gelatin spinning solution formulations and customizing gelatin biofibers. Gelatin biofibers naturally have a whitish color, but we explored color customization during two processes, post-production and spinning solution preparation. In post-production, we used the last multipurpose bath of the machine to fill it up with a solution containing diluted turmeric powder, resulting in yellow biofibers. During spinning solution preparation, adding genipine, a bio-based crosslinker, resulted in the biofibers taking on a green hue. Crosslinkers like genipine serve as binding agents, bonding molecules to enhance the strength and stability of the fibers. In the case of gelatin biofibers, the addition of genipine resulted in various shades of green, with the darkness of the color corresponding to the higher concentration of the crosslinker, indicating greater strength. We performed a preliminary tensile test of gelatin biofibers with and without genipine crosslinker. The results showed that the cross-linked biofibers had a greater strength compared to pure gelatin biofibers, whether in dry or wet conditions. Dry gelatin biofibers reached about 71 megapascals compared to PLA's 38 to 50 megapascals. Continuing with customizing the gelatin biofibers, we used the last multipurpose bath of the machine to test coating UV-sensitive photochromic paste on already dry gelatin biofibers. This process successfully converted the biofibers into UV-sensitive ones. Since we used a non-bio-based pigment for this initial test, future work could explore the use of bio-based coating alternatives for sensing applications. Our machine enables the customization of fiber diameter by adjusting both the extrusion rate and collector speed. Increasing the collector speed has shown to yield smaller fiber diameters, some as fine as 0.03 millimeters. For more details regarding the correlation between the speed and diameter values, refer to our paper, which also covers more details about the machine walkthrough, fiber spinning considerations, and more of our material exploration with a series of gelatin biofiber material formulations. Now let's explore some practical applications of these biofibers in smart textiles. We use weaving as a textile technique to demonstrate how we envision seamlessly integrating biofibers into textile structures. For instance, we use twill and waffle weaves to make moisture and pressure sensors respectively. Our example applications primarily focus on the dissolving quality of biofibers to promote end-of-life sustainability, enabling conductive material recycling or reharvesting, as well as using dissolving to enable interaction in the smart textile. In this example of a single-use woven moisture sensor, wetting the gelatin biofibers when the sensor is in use creates an electrical pathway between two embedded silver threads. At the same time, the gelatin biofibers begin to swell and eventually dissolve. The change in color is attributed to the genipine present in their spinning solution. When exposed to a solvent solution, the genipine causes the biofibers to turn to a bluish hue. Finally, the dissolving of the biofibers enables the recycling and reharvesting of the conductive and not conductive threads. In this example, dissolving was used to intentionally etch a trace in the cloth. We created a two-layer swatch with gelatin biofibers on top and conductive yarn at the bottom, allowing for isolation and layering. Leveraging the gelatin biofibers dissolving upon exposure to a solvent solution, such as hot water, we can intentionally reveal the conductive layer beneath. This application shows the potential for on-body etching of flexible surfaces during circuit prototyping on cloth. By incorporating biofibers to create a soluble top layer, designers can easily etch traces on the cloth, aiding in the prototyping process and reducing waste. These applications are proof of concepts demonstrating what we can do with gelatin biofibers that are produced with our machine. Please refer to our paper for other applications. Our paper contributes with the development of an open-source, low-cost, and customizable Desktop Biofibers Spinning Machine, a series of gelatin biofiber material formulations, example applications showcasing practical use of the machine in producing biofibers towards sustainable smart textile design, and insights derived from fiber production, wet spinning processes, and interdisciplinary fiber design. Regarding the latter point, creating spinning solutions for biofibers isn't straightforward and demands expertise from diverse fields, notably green chemistry. While our study focused on gelatin biofibers due to their customization possibilities, we are open to collaborations to explore making biofibers from other biobased spinning solutions using our machine. Engaging with people outside our field sparked fresh ideas. For instance, talking with a chemist specializing in biocompatible materials for tattoos introduced us to genipping as a natural crosslinker. Unexpectedly, using genipping led to outcomes we leveraged in our interactive applications. When cross-linked gelatin biofibers encounter a non-gelatin solvent, they change color, swell, and become elastic in a wet state. We found this quality intriguing and worthy of further exploration for interaction. Lastly, we highly recommend exploring our paper for deeper insights into our approach to sustainable smart textiles, as well as our machine's limitations and future direction. This is the QR code to our GitHub repository, and please let us know if you have further questions. Thanks.